Hello, and welcome to this presentation on a brief introduction to differentiation. Here we're going to overview differentiation in a very pragmatic way, looking at its essence and purpose, and also how to use classical differentiation techniques to find standard forms. A brief overview of the calculus. The calculus is a branch of mathematics that deals with changing quantities. It was invented to solve problems not solvable with algebra or geometry. The calculus was developed independently by Isaac Newton, a scientist, and Gottfried Leibniz, a mathematician. This has since stimulated many new directions in mathematical study. Because both Leibniz and Newton published their work around similar times, but had used different notation, we find that even in modern day texts, these two notations still exist, so we need to be aware of these, and we'll highlight these in this presentation. There are actually two branches of the calculus. The first one is called differential calculus, and that tries to answer questions relating to speeds of moving objects. For example, how fast will the Earth be moving around the Sun on July the 4th? And the second branch is called integral calculus. This was invented to answer questions relating to what is the area of a shape with curved sides. We are only going to look at differential calculus within this presentation. Differential calculus. Differential calculus, also known as differentiation, is a very powerful mathematical technique used by engineers and scientists. Differentiation is used for analysing the way in which functions change, often with respect to time. For example, Newton's laws of motion and the laws of aerodynamics are expressed in terms of differential equations. Applications of differentiation include analysing stresses in loaded beams, temperatures in an industrial chemical, the rate at which a vehicle's speed is increasing or decreasing, and the torque on an aircraft propeller blade. Other applications include calculating the rate of change of current in an electrical circuit, and the voltage in a transmission line, the charge in a capacitor, and bacterial growth. As you'll see in the following slides, essentially differential calculus determines gradients at points on curves. That's the essence of the technique. Unfortunately, a thorough knowledge of algebra, particularly the laws of indices, is required to underpin use of differentiation. We're going to initially take a very pragmatic approach to looking at differentiation, and the following few slides all relate to try and understand what differentiation actually does. And the essence of it is that it finds gradients at points on curves. So we're going to show that here. So this graph plots a quadratic equation of the form y is equal to x squared minus 4x plus 4. And what we're going to do initially is to estimate the gradients at 3 points on this curve. At point A, at point B, and at point C. So we're going to do that by adding tangents to each of those positions and then working out the gradient of the tangent at that point. So here's my solution to exercise 1, trying to calculate the gradients at points A, B and C on our quadratic curve y equals x squared minus 4x plus 4. So at point A, I tried to draw the best tangent I could to that point here. Then I took 2 points on that tangent, here and here, and I drew a right angled triangle, and I worked out the coordinates of the vertical side of the triangle, 9, and the horizontal side, minus 1.5. I added these values to my table, so the change in y was 9, the change in x, I called it minus 1.5 here. So 9 divided by minus 1.5 gave me minus 6. The gradient at point A is estimated to be minus 6. Negative because it's a negative slope. By inspection, looking at B and drawing a tangent to point B, it's obviously a horizontal line. So by inspection, the gradient at B is 0. At point C, again I tried to draw the best tangent I could to point C, and again I took 2 points on that tangent line, and I worked out my vertical distance between the 2 points, my horizontal distance between the 2 points, and again dividing the 8 by the 2 in this case gave me 4. So the gradient at C I estimate to be a positive 4 value. Here we're given a cubic equation, y is equal to x cubed minus 3x plus 5, and we're given 4 points on the curve at which we're asked to work out the gradients. So here's my solution to exercise 2. The equation plotted is y is equal to 3x cubed minus 3x plus 5. Now by inspection I can immediately say the tangent line at A and the tangent line drawn at C are going to be 0. So by inspection the gradients at A and C are going to be 0. At point B I try to draw the best tangent line I can through point B, and again then taking 2 points on that tangent line, I've taken the point of here and here. I work out my vertical distance between the 2 points, 6 in this case, my horizontal distance, which is minus 2. I'm using negative because it's a negative slope there. So 6 divided by minus 2 gives me a slope of minus 3. So I estimate the gradient at point B is negative 3. Finally, looking at point D, I'm trying to draw my best tangent line I can through point D, and then take 2 points on the line, actually taking the point at D and this point down here. I can work out my vertical distance between the 2 points, it's 5, and my horizontal distance is 0.5. Again, dividing the 5 by the 0.5 gives me a value of 10. So I estimate my gradient at point D is positive 10. Example 1a. In this example, we're going to try and find the differential coefficient of a given function, and that function is y is equal to x squared. We're going to use what's called classical differentiation to find this differential coefficient. So in the classical differentiation approach, we're going to let delta x be a very small increment in the x direction and delta y be a very small increment in the y direction. So we're going to consider the coordinates of point Q being a small distance away from point P, as shown in our diagram. Here's our curve, y is equal to x squared, and I've got point P here at the x distance in and the y distance up on my xy diagram. And I've also got point Q here, which is x plus delta x on the x-axis and y plus delta y on the y-axis. And as it says on the left-hand side, the delta x and delta y terms are thought of very, very, very small values. I've drawn them quite large here because I needed to for illustration purposes, but think of them as being really, really small values, that q is very, very close to p on the y is equal to x squared curve. Example 1a continued. So therefore, point Q can be defined in its x and y terms as y plus delta y on the left hand side is equal to x plus delta x squared, because the function we're looking at is y is equal to x squared. If I expand the brackets on the right hand side, don't forget x plus delta x squared means x plus delta x multiplied by x plus delta x in the brackets. Expanding that as a binomial bracket, I will get x squared plus x delta x plus x delta x plus delta x squared. And I'm sure you can expand that bracket with your crab claw or your smiley face method. Just tidying that up on the next line, I get the y plus delta is equal to x squared plus 2x delta x plus delta x squared. Now we know from the original equation that y is equal to x squared. That was given to us in the original question. So in the above equation, I could cancel the y on the left hand side with the x squared on the right hand side because they're equal to each other from the equation initially given. So the above equation can simplify to delta y is equal to 2x delta x plus delta x squared. If I divide throughout by delta x, so every term now is being divided by delta x, on the left hand side I get delta y divided by delta x, I get 2x delta x upon delta x on the right hand side plus delta x squared upon delta x. If I simplify the terms, left hand side I get delta y upon delta x, on the right hand side the 2x delta x over delta x cancels to simply give me 2x, and the delta x squared upon delta x cancels to give me the plus delta x. So what we do now in this classical calculus process is assume that the delta x term tends to 0. So delta x, which is already very small, now is tending to almost nothing. It cannot be 0, but it's so close to 0 that we couldn't measure how close it is. So think of that in your mind. It's a very, very small value. So in looking at the above, I can now simplify the equation. On the left-hand side, I usually write the delta y upon delta x as dy by dx, as we tend to 0. And on the right-hand side, I simply get 2x, because the plus delta x term, if it tends to 0, will be irrelevant compared to 2 times x. So what's called the differential coefficient of y is equal to x squared in this case is written as dy by dx equals to 2x. And the dy by dx is the gradient equation or the slope equation for the original function y is equal to x squared. What we've done there is use classical differentiation to end up with the dy by dx. Example 1b. The process we're going to use here is almost identical to that of example 1a. We're going to find the differential coefficient of a function, but this time the function given is y is equal to x cubed. All the assumptions are the same. The delta x is a very small value in the x direction, the delta y is a very small value in the y direction. And we're going to go through exactly the same classical differentiation process with the y is equal to x cubed term here as we did with the y is equal to x squared in example 1a. If you do that, you end up with the dy by dx, the differential coefficient, given as 3x squared. So y equals x cubed is the original function given to us, and when we differentiate it through the classical differentiating process, we end up with dy by dx is equal to 3x squared. Example 1c, again we're going to use exactly the same process on the previous slides to find the differential coefficient, but this time of the function y is equal to 4x squared. Again I've got my 4x squared term here. All the assumptions are the same about the delta x and the delta y, so going through the same classical differentiation process, we end up with a differential coefficient dy by dx is equal to 8x. So given the original function y is equal to 4x squared, when we differentiate it with our classical differentiation, we get the dy by dx is equal to 8x. Now example 1d asks us to find the differential coefficient of the function y is equal to x squared minus 4x plus 4. Now that was the original equation we were given on the exercise 1 a few slides prior to this one, where we worked out the gradient at 3 points using a graphical method. What we're going to do here is use the classical calculus to end up with a dy by dx function, and we're going to use that to find the gradients on the curve of the 3 points a, b and c we've already worked out graphically. So all assumptions are the same again, just that the equation is different. The y is equal to x squared minus 4x plus 4. If I go through the classical differentiation, I end up with a differential coefficient of dy by dx is equal to 2x minus 4. Example 1d continued. Purely for reference here, I've showed the classical differentiation for calculating the dy by dx for the function y is equal to x squared minus 4x plus 4. Again, if you follow the steps through here, exactly the same steps we used in the previous example, you'll end up with a differential coefficient of dy by dx is equal to 2x minus 4. I'll just leave that there for your reference. Example 1d continued. So what we're going to do now is compare the estimated values we had in exercise 1 for therefore the equation y is equal to x squared minus 4x plus 4 at the 3 points of A, B and C on our diagram, we're going to compare those results we've got in the table on the right hand side with the results from the differential equation we found on the previous slide. So, from the previous slide, our differential coefficient, dy by dx, is equal to 2x minus 4. So what we're going to do now is put the values of x into the equation at which location we want to find the gradient. So on our diagram, point A here is at an x value of minus 1. So let x equals to minus 1 and simply put the value of minus 1 in the equation 2x minus 4. If you do the arithmetic on that, you'll find that the gradient, the dy by dx, is equal to minus 6. From our graphical method, we found the gradient was minus 6. Now we're going to find the gradient at point B, and the x value at point B was 2 on our diagram. So all we do now is make the x equals to 2 and put 2 into the dy by dx equation. So it's 2 times 2 take away 4 gives us 0. So the gradient at B, which we can see by inspection, is 0, is the same on the graphical method as from the differential coefficient. And finally, we want to find the gradient at point C. Now C occurred at an x value of 4. So now we let x equals to 4, put that into our dy by dx equation and do the numbers on that. We get a gradient of 4, positive 4. And again, from our graphical method on the previous slide, we found the gradient was positive 4. So although this is no proof of the calculus, it certainly is a good indication that our graphical method and the analytical method, finding the differential coefficients dy by dx, appears to give exactly the same results. It's quite encouraging. The sheer beauty of the differential calculus approach is that I could now find the gradient at any value on the curve by putting the value of x into the dy by dx equals to 2x minus 4 equation. Whereas the graphical method is quite cumbersome, not necessarily accurate, but it's been quite accurate in this particular case, and it's time consuming. Example 1e. We're now going to find the differential coefficient of the function y is equal to ax to the n. So again, using classical differentiation, all the original assumptions are the same, and there's our curve y is equal to ax to the n. If you apply the classical differentiation process to the original function y equals ax to the n, you end up with a differential coefficient of dy by dx is equal to a n x to the n minus 1. In other words, a, which is a constant, multiplied by n, another constant, multiplied by x to the power of n minus 1. If we now look at a summary of all the results on the previous slides for all the y equals function of x examples we were given, and the dy by dx differential coefficients we calculated, we find that we have y is equal to x squared differentiates to dy by dx is equal to 2x, y is equal to x cubed differentiates to dy by dx equal to 3x squared, y is equal to 4x squared differentiates to dy by dx equal to 8x, and the y is equal to x squared minus 4x plus 4 differentiates to 2x minus 4. What you notice is they all follow the standard pattern. Given y is equal to ax to the n, our polynomial, they all differentiate to the form of dy by dx is equal to a times n times x to the n minus 1. If you take just one term, for example, take the third term down, the y is equal to 4x squared, that's of the form y equals ax to the n, where the a is equal to 4 and the n is equal to 2. If you follow the pattern through for the dy by dx, you'll get a times n, so that'd be 4 times 2 is 8, x to the 2 take away 1, that will give you x to the 1, so we get 8x. Just for your reference on this table, at the top of the second column I use notation dy by dx or f dash x. Referring back to what we said at the beginning of the presentation, don't forget that both Leibniz and Newton were involved with creating the calculus, and that there are two notations used, and the two notations are shown here. The dy by dx is Leibniz notation, and the f dash x is the Newton's notation, also called functional notation. Continue with our summary of polynomials here. I've added certain values to this slide in purple to try and illustrate how the form of the y equals ax to the n, the original function we're given, becomes the form dy by dx equals anx to the n minus 1, our differential coefficient. So if we take the first line of the table, we've got a form y equals 1x squared. I've added the 1 here. Now that's of the form y is equal to ax to the n. We're told that the differential form, dy by dx, is the form an x to the n minus 1. So a times n, and then take 1 off the index. So looking at my dy by dx form on the right hand side, we get 1 times 2, it's a times the n, that's 2, take 1 off the index, so that goes from 2 to 1. So our solution is 2x to 1, or simply 2x. You take the second line and the next function, we've got y is equal to 1x cubed. And again, we've got the form ax to the n, where a is 1 and n is 3. So our differential coefficient, dy by dx, will be the 1 times the 3 is 3, and take 1 off the index gives us 2. On the next line, we've got the function y is equal to 4x squared, where a is equal to 4 and n is equal to 2. So our dy by dx, following the pattern, we'll get a times n, 4 times 2 gives us 8, and take 1 off the index, that becomes x to the 1, or simply x. Looking at now the last row of our table, we've got 3 terms on the right hand side, but we take each term individually and we make them into the form ax to the n. So we've got y is equal to 1x squared, so that's ax to the n. Take away the 4x to the 1, so that's of the form ax to the n, plus 4x naught. Notice I've written the x to the naught against the 4 because x to the naught is 1, anything to the power 0 is 1, so I've still got 4 at the end for my third term, but it is of the form ax to the n now, so I can differentiate it. If you follow the pattern through for each of the terms, taking the first term, you'll have 1 times 2 is 2x to the 1, taking 1 off the index. For the second term, following the pattern through, you'll have minus 4 times 1 gives you minus 4. X to the 1 take away 1, that would give you x to the 0, and don't forget anything to the power 0 is 1, so we simply get minus 4. And looking at the last term, we've got 4 times 0, following the pattern through of a times n, obviously that term will now disappear. So we just simply end up with dy by dx is equal to 2x minus 4. I hope that's helped a little bit with your understanding of how to use the polynomial functions. We're now going to revisit exercise 2, which was our cubic curve, and this time we're going to solve for the gradients at a, b, c and d using differentiation. Remember on a previous slide we were given the function y is equal to x cubed minus 3x plus 5, and graphically we went through trying to find the gradients at these points, and we noted the gradients in our table down here on the right hand side. What we're going to do now is use the standard differential for ax to the n. We're going to find the differential coefficient, find the expression for dy by dx, and use that to find the gradients at a, b, c and d, and then compare them to the graphical technique. So given the expression y is equal to x cubed minus 3x plus 5, that's the equation of our line, and I'm going to use the standard derivatives from the table on the previous page. We know that ax to the n differentiates to give you an x to the n minus 1. So taking the x cubed term, following the pattern, that's 1x cubed, that differentiates to 3x to the 3 take away 1, that gives us 3x squared. Taking the second term of minus 3x, that differentiates to minus 3 times 1, x to the 1 take away 1. That gives us minus 3, because the x to the 1 take away 1 is 0, and x to the 0 is 1. When you differentiate a constant, the plus 5, that always disappears because that's multiplying by 0 if you follow the pattern through. So we end up with a dy by dx differential coefficient of 3x squared minus 3. That's our slope equation or our gradient equation. So we're going to now use this to find the gradients at points A, B, C and D. So looking at point A first of all. Point A occurs at a value of x of minus 1 on our graph. All we do now is put the value of minus 1 into the dy by dx equation and evaluate the answer. So 3 times minus 1 squared would be 3, take away 3 would give us 0. In other words, from our differentiation process, the gradient at A is 0. And we can see by inspection it's 0, that's what we found from our graphical technique, because drawing a horizontal line through A for the tangent means there's no slope, no gradient. If we want to work out the slope at B, we need the x value for B, and that's x is equal to 0. All we do now is put the value of x into our dy by dx equation and evaluate the answer. It's minus 3. We get a negative 3 slope at B. And that's what we got from our graphical method, negative 3. If we want to find the gradient at point C, that's an x value of 1. All we do now is put the value of 1 into our dy by dx equation, evaluate the answer, it gives us 0. We can see it's clearly 0, and we found that from our graphical method. And finally, to find the gradient at point D, that would be x is equal to 2. We simply put the value of 2 into the dy by dx equation, and that gives us plus 9. From our graphical method, we actually estimated the gradient there was a positive 10. So we were very close with our graphical method, but the differential method is the correct answer. So the gradient there is actually plus 9. But we were a reasonable estimate with our graphical method. The sheer beauty of the differential method is that now I can find the gradient at any value of x by simply putting the value of x into the dy by dx equation of 3x squared minus 3. The graphical method, although nice and visual, is quite cumbersome, it's quite time consuming, and it's not necessarily particularly accurate. So in essence, wherever you have an equation to a curve in the form y equals ax to the n type format, differentiation is the best method, the most accurate method to use to evaluate gradients at points on curves. What I'm going to try and show on this slide and the following slides are differential coefficients for other common functions such as sine, cos, etc. So if we take the sine curve, this is a typical sine curve here, hopefully you're familiar with the sine curve. What I'm going to show is that the differential coefficient of the sine curve, the dy by dx, is actually the cos x curve. Now looking at the sine curve, at this position here, at the value of 0 on the x-axis, 0 radians in this case, that's a maximum gradient for the curve. As soon as we move away from 0 to the right along the x-axis, the gradient starts to drop off. Now on the cosine curve, the dy by dx curve, you can see it's a peak there, it's a maximum value. The dy by dx curve is showing you the gradient change. The y equals function of x curve is showing the actual function we're plotting. So in the gradient curve, the dy by dx curve, we've got a maximum value there on the cos curve. And that would be correct for the gradient at point O on the diagram for the sine curve. If we move to the angle pi upon 2, we find that point A here would have 0 gradient, because if we draw a tangent to point A, we get a horizontal line. Now on the dy by dx curve, the cos curve, we get 0, which would be correct. If we now go to the point B on the sine function, that's at angle pi here, we should have a maximum negative value, because it's a maximum negative gradient at that point. And on the dy by dx curve, the cos curve, we get a maximum negative value on that curve. If we look at point C on the sine curve, which is 3 pi upon 2, we should get 0 gradient, because again a tangential line drawn to C would be a horizontal line. And this is exactly what we get on the dy by dx curve, the cos curve, we get 0. And finally at point D, we're now starting the cycle over again, we get a maximum positive value, and on the dy by dx curve, the cos curve, we get a maximum positive value again. So this is no proof, but it does indicate that the cos curve in this case is a differential of the sine curves. It gives the gradient of the sine curve as we move along the x-axis. Okay, looking at the cosine or cos curve here. We've again plotted the y is equal to cos x on the top of the page here, and we're given that the differential coefficient of cos x dy by dx is equal to minus sine of x in this case. So what we've got drawn here on the dy by dx curve is a negative sine x curve. Now if we look at the original y is equal to cos x curve, we've got 0 gradient at the 0 position on the x-axis, and the negative sine x curve gives us the dy by dx of 0, so that was correct. At point A on our cos x curve, which is at half pi on the x-axis, we have maximum negative gradient, and on our dy by dx minus sine x curve, we've got the maximum negative value of that curve. At point B, which is at pi radians, we should have 0 gradient, and we've got 0 gradient on our dy by dx curve, the minus sine x curve, it's 0 there. If we look at point C on the y equals cos x curve, we should have a maximum positive value there, and on our dy by dx curve, the minus sine x curve, we've got a maximum positive value there. We then look at point D on the y equals cos x curve, which is at 2 pi radians. We should see we get 0 gradient, and that's exactly what we get on the dy with x curve, with a minus sine x curve. So again, no proof here, but it does indicate that the differential of the cos x curve is minus sine x. Differentiating a natural logarithm curve. What I've drawn here is various values of y is equal to ln, natural logarithm, of a times x. Now we're given that the differential coefficient of dy by dx for y equals ln ax is actually 1 upon x, or x to the minus 1. So what that means is that for any value of au, so ln ax is, a is 1 here, ln 2xa is 2, ln 3xa is 3, and so on, for any value of ln ax, the solution is always x to the minus 1. And if you look at the curves here, I've just drawn a tangent to this point here, but I think it's clear to say to all the curves, the ln 1x, 2x, 3x, 4x, and so on, the tangent is exactly the same in all cases. And I said we're given that the tangent is actually the 1 upon x, or x to the minus 1 value. So just take a moment to reflect on that. Whatever the value of a in the y equals ln ax equation, the solution for dy by dx, the gradient, is always x to the minus 1, irrespective of the value of a. The final curve we'll look at is e to the x. So y is equal to e to the x, and it's plotted here. This is the y is equal to e to the x curve. This is actually y is equal to e to the minus x. So y is equal to e to the x. We're given that the differential coefficient dy by dx is actually e to the x. This is a quirk of this curve. For a given value of y of 4, if you differentiate the y is equal to the x, you will find that the gradient is also 4. And that's a quirk of the y is equal to e to the x curve. So drawing together the information from the previous slide, we can actually produce what's called a table of standard derivatives. On the left-hand side of the table, I have the y, or the function of x, and on the right-hand side, I have the dy by dx, or the function dash x. So now we know that if we have a polynomial of y is equal to ax to the n, the differential coefficient dy by dx is a times n times x to the n minus 1. If we have a function y is equal to sine ax, the differential coefficient will be a cos ax. If we have a y is equal to cos ax function, the differential coefficient will be minus a sine ax. If we have an ln ax function, then the differential coefficient is always 1 upon x, or x to the minus 1. If we have a function y is equal to e to the x, the differential coefficient is e to the x. And if we have a y is equal to e to the ax, the differential coefficient will be a e to the ax. So this is a table of standard derivatives we can refer to when we're doing differentiation work. Obviously there are more standard derivatives that you can find if you're looking at the reference sources and so on, but it's usually the first few lines of the table that are the most common ones that we'll be dealing with. I'm hoping this brief presentation has given you an insight into what standard derivatives are and hopefully how we're going to use them. You do not really need to worry about deriving them for the work we're going to do. It's more about using the tables and being able to manipulate the equations using algebra and indices and so on. So the next presentation will build on this and actually show us how to apply the table of standard derivatives. But hopefully it's given you an overview as to what differentiation is. It's basically finding gradients at points on curves, and in a context that might relate to displacement, velocity, accelerations you'll see later on. Here's the bibliography used to generate this presentation. I would strongly encourage you to refer to some of these reference sources. They're very good reference sources specifically for technician engineering students. I hope this presentation has been of interest to you, and thank you for viewing.